It's 11 o'clock on the 5th Sunday of a month, our special Chai and Wai sessions. And this month, anyway, we've had Chai and Wai on every Sunday because it's November, Nobel Prize time. And in the last of our series on the Nobel Prizes of the year, we have Lankeswar Dey, who's going to tell us the story about the black hole, rather a monster black hole at the center of the Milky Way. Lankeswar is an integrated PhD student at TIFR. By now, I think you know that our Chai and Wai Nobel Prize talks are given by our graduate students. And Lankeswar works in the Department of Astronomy and Astrophysics. He came to us from a small college in Murshidabad, but has been doing some fantastic work over here. In fact, a few months back, there was this really big press release about a binary black hole blazar. That's like a tongue twister. OJ287, and Lankeswar and the group he works in played a very important role in this. So he works in black hole mergers, gravitational waves, and all this. And he is absolutely the right person to take us through the story of the second part of the Physics Nobel Prize, the discovery of the black hole at the center of the Milky Way. So over to you, Lankeswar, all yours. And for those who are watching us live, welcome, still live. Maybe we will go back to having physical programs in 2021. Let's hope COVID cooperates. And remember to post your questions on the chat. So you can put it on the YouTube chat. And we have a couple of us who are monitoring the chat, and we will tell Lankeswar what the questions are, or we will take them at the end, both on Facebook and on YouTube. Yes, please do tell us if you can hear us, not hear us, give us your feedback on chat, because that's the only way we can communicate with you. So all yours, Lankeswar, over to you.
Thanks, Arnav. So, yep. So good morning, everyone. So as you can see in the title, today we'll be talking about hunting black holes, but not just any black holes, very massive and monster black holes. And that also sits very close to us, that is in our galaxy. Okay, so let's get started. So this year, Nobel Prize in Physics was awarded to 3 scientists. Half of the Nobel Prize was awarded to scientist Roger Penrose for the discovery that black hole formation is a robust prediction in the general theory of relativity. And on 15th November, Chai and Wai session, Sharonno gave a fantastic talk about that. And the other half of the Nobel Prize is shared between 2 astronomers, Reinhard, Genzel, and Andrea, Ghez, for the discovery of a supermassive compact object at the center of our galaxy, and which is most likely a supermassive black hole. So in today, I'll be focusing about this part of this Nobel Prize, like how they find that there is a supermassive compact object in our galaxy. Okay, so before talking about the supermassive black hole in our galaxy, let's take a look what is a black hole and what are their properties, how do they behave. So what is a black hole? A black hole is a region in the space-time where gravity is so strong that nothing can escape from it. Okay, not even light can come out from it. And if you see this word black hole to an expert theoretician, he or she will see something like this in his mind, that okay, there is space-time, and the space-time is curved due to very high density of matter, and this curvature goes to infinity at the center, and there is this borderline here shown by this red curve, and if something falls into this within this borderline, then it will go to the center and it will never be able to come back, whether how fast it moves. Even light cannot come out from it. Okay, but if someone asks me what is a black hole, I see something like this, because I am not that an expert of black holes. Okay, so to me, black hole is like this spherical black region in the space, and nothing can come out from this region. And for today's purpose of for today's talk, this kind of a picture of black hole is enough for us. We don't go into the details of the space-time curvature and anything. Just imagine black hole as a region from which nothing can escape. Okay, so let's talk a little more about the black hole. So every black hole has an associated radius with it, which is called the Schwarzschild radius, and that determines the point of no return. And the Schwarzschild radius mostly depend on the mass of the black hole. And if the black hole is spinning, then it can also depend on the spin. But for today's talk, we'll be ignoring the spin of the black hole. So we'll only consider about the mass. So if a black hole only has a mass and no spin, then the Schwarzschild radius is given by this formula. This Rs is the Schwarzschild radius, is equal to twice gm by c square, where g, capital G, is the gravitational constant, capital M is the mass of the black hole, and c is the speed of light. So in this picture, you can see a visualization of a black hole. At the center, this red point is the singularity, or this is the black hole. So actually, it doesn't have any dimension. It is just a point, but to show you, it is shown as a like red dot. And at a there is a spherical surface at a radius Rs, which is the Schwarzschild radius, and this spherical surface is called the event horizon, and this determines that if something goes into the event horizon, it cannot come out. So this is the boundary line. This is the Laxman Rekha. If you go in, you cannot come out. But I just want to say that this event horizon, this is just an imaginary surface. Okay, there is no physical existence of it. So if you are falling into a black hole, so you don't have to worry. You will not collide with this surface. And so this is the overall picture of a black hole. And anything can be a black hole. Anything. So if you just have any object, and if you know the mass, you have to calculate what is the corresponding Schwarzschild radius for that mass. And if you can somehow squeeze that object to that size of its Schwarzschild radius, then it will become a black hole. Because at that, if you can squeeze it, then gravity wins, and the gravity will is so strong that everything will be collapsed at a single point. So the Earth on which we are living, the Earth can be a black hole. Okay, so if we can squeeze the whole Earth into the size of a sugar cube of a size of around 1 centimeter, then our Earth will be a black hole. The sun can be a black hole. The mass of the sun is 2 into 10 to the power 30 kg. That is 30 zeros after 2. This much kg. Okay, and this whole mass, if you can somehow squeeze into the area of a sphere with radius 3 kilometers, that is about the size of this whole Kolaba area, then the sun will also become a black hole. And just remember this mass of the sun, because we will use the mass of the sun as our unit of mass. Because in astronomy, we deal with very huge, massive objects. So we always cannot write, okay, this many zeros of kgs. Okay. So how do we use like m sun? This is the solar mass as our unit. And if something is 10 times more massive than our sun, then we will say, okay, the mass of this object is 10 solar mass, and so on. So anything can be a black hole if we can squeeze it to its Schwarzschild radius size. And black holes come in different sizes. It can be small, it can be medium, it can be very big, huge. Okay? And they are broadly divided into 3 categories. The first one is a stellar mass black hole, and those black holes which has mass less than around 100 times the mass of our sun, those are called stellar black hole. And then comes the intermediate mass black holes, those black holes which has mass from the range of 100 solar mass to a million solar mass, those are called intermediate mass black holes. And then comes this big guy, supermassive black hole. Okay? So if the black hole has a mass more than million solar mass, then we call it a supermassive black hole. And it can go up to tens of billions of solar mass. Okay? And in today's talk, we will not talk about these small fries. Okay? We'll talk about these big supermassive black holes, and we will search whether our galaxy has a supermassive black hole at its center. So how does this idea of supermassive black holes come to the scientist's mind? Okay, so let's talk about a little history of supermassive black holes. So the story starts with an astronomical object which name is 3C273. Okay. It was first discovered as a radio source, a very bright radio source actually, and it was thought it was like a star. If you can see in this picture, it just looks like a star. And people thought it is just like a star, but some of these properties were not exactly like a star. So they name it quasi-stellar object. So yeah, it is star, something like star, but not exactly star. And in short, it was called quasar. And the people thought that it is a bright source in our galaxy itself. But in 1963, astronomer Martin Smith, he showed that this object 3C273 is not within our galaxy, and it is very, very far away from us. It is billions of light years away from our galaxy. And this was a very surprising result to all the scientists. So I will just want to talk about how Martin Smith calculated the distance of this source. So to calculate the distance of the source, what he used is a very basic concept in physics, which is Doppler effect. So we all know Doppler effect, and it is most we know in about sound. So if a car is approaching an observer, and in that case a car is blowing a horn, then you will find that the frequency of the horn, it is increasing and increased than the original one. But if the car is moving away from an observer, then you will find that the frequency of the horn is less than what is actually be. So if the car is approaching you, then it will be like beep 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 beep. It will be very fast. But if it is going away from you, then it will be like beep beep beep. Okay. So what happens if an object is moving towards you, its frequency increases, and if it is or wavelength decreases, and if it is moving away from you, its frequency decreases. Okay, and this is not only true for sound wave, this is also true for light. Okay, so if a source of light, if it is going away from you, then also the light frequency of the light will be decreased. And the same principle was used to calculate the distance of this source 3C273. So how it was done, let's take a look. So we all know that when a white light passes through a prism, it gets split into different colors, like this rainbow color, and this different colors means different wavelengths. So if from a source some light is coming, and if you put something like prism, and then you can actually measure at what wavelength how much amount of light is coming, and if you plot it, you will get something which is called spectrum of this source. So this is what the spectrum of this source 3C273 looks like. So in the x-axis, this is the wavelength, and this is the wavelength in the visible regime. This is from like violet to red. From left side it is violet, and to right it is red. And this is the intensity, or how bright the source is in that particular wavelength. And you can here see some very high peaks, very bright peaks, right? Here. So this peaks implies that at this particular wavelength, lots of light are coming. And these are called emission lines. So by studying these emission lines, we can actually say what kind of materials is there from in that source from which light is coming. And the Martin Smith find out that all these emission lines, they are for this source, they are actually shifted by a factor of 1.16. So this line is called hydrogen alpha line. This line comes from element hydrogen. So if in lab if we measure this line, the frequency or the wavelength would have been around 6,600. But for this source, the wavelength is actually around 7,600, which is around 1.16 times larger. And this is true for all the emission lines. It is also true for this. And this shift is shown by this red arrow. So actually it should have been here, but it is here. Actually it should have been here, but the H beta it is here. Okay, so all the wavelength increases, and we know from the Doppler effect, if an source is moving away from us, then the wavelength increases or frequency decreases. Okay, and the factor 1.16 by which it is increased, we can actually calculate how fast this source is moving away from us. And this, if we calculate the velocity of this source, it's turned out to be 0.15 times the speed of light. That is 15% of speed of light. That is a very huge velocity. Anything within our galaxy cannot move that fast. So this is outside our galaxy, and it is going away from us very fast. So why it is going away from us? So that here we got the velocity of this source, but from velocity how you get the distance. So the source is moving away from us because the universe is expanding, and every object in our universe is moving away from each other because the universe is expanding. And the farther away the object is from us, the faster it is moving away. So if it is close to us, it is moving away very slow, but if it is very, very far away, it is moving away at a very fast speed. Okay, and this 3C273, this source is moving away at a 15% speed of light, and that implies from this velocity of at which it is going away from us, we can actually calculate what is the distance. and the distance turned out to be around 2.5 billion light years. So that is very far away. So this is how the distance of the source was measured, but this was a very puzzling result because, as I said earlier, this was a very bright radio source. Okay, and if it is that far away and it is still that bright, that means the actual brightness, okay, the actual brightness of this source is very, very high. The actual brightness turned out to be around 1,000 times brighter than our whole galaxy or whole Milky Way. So there is an object which is 1,000 times brighter than a whole galaxy. That was like very surprising to all the community, science community. And it doesn't end here. There is more surprise coming. Okay. So in this plot, what you can see in the x-axis, there is this time, this date in year from 1960s to 2000, and the y-axis it is flux, which you can say the brightness of this source. Okay, and here the scientists saw that the brightness of this source vary quite a bit within a month. Okay, and what does this signify? The brightness varies within a month. That means that the source, the region of the source from which the light is coming, has a size which is less than the distance light can travel within a month. Okay, so that means from this source the light is coming from a region which has a size around few times our solar system. Okay, so not only the light is 1,000 times brighter than our whole galaxy, but also it is coming from a very small region which is few times our solar system. So everyone was surprised how from a very, very small region like this so much energy can come out. What sort of process can generate like such huge amount of energy? And everything was wondering, okay, what is the reason? What is the reason? And even the famous scientist George Gamow like changed that nursery rhyme "Twinkle Twinkle Little Star" to like something like this: like, "Twinkle Twinkle Quasi Star, biggest puzzle from afar. How unlike the other ones, brighter than a billion suns. Twinkle Twinkle Quasi Star, how I wonder what you are." So not only George Gamow, every other scientist, everyone was wondering what are these stars, what are these quasars, okay, and how this huge amount of energy is coming from such small region. Okay, so there was lots of proposal, lots of discussion, lots of debate, but after lots of debate and discussion, everyone agreed that there must be a supermassive black hole involved, and only a supermassive black hole is the reason to produce such a huge amount of energy. But we know that nothing can come out from a supermassive black hole, right? So how supermassive black hole is producing so much of energy? And the reason is the supermassive black hole is not alone. Okay, there are lots of dust and gas around this supermassive black hole, and which is falling into the supermassive black hole. The supermassive black hole eating those dust and gas which is around it. And this dust and gas which is falling into supermassive black holes forms an accretion disk, forms a disk-like structure. And the accretion disk, which is very close to the supermassive black hole, and due to friction, they go to very high temperature. Okay, I mean hundreds of millions of Kelvin, and because of this very high temperature, this accretion disk actually can produce this huge amount of energy from a very small region, and it can outshine a whole galaxy. So this was explained that okay, a supermassive black hole with an accretion disk and eating lots of matter can actually produce those huge amount of energy from a small region. So then it was established that 3C273, this source has a supermassive black hole at its center. And after 3C273, more and more galaxies were found to have supermassive black hole at their center. So then these two scientists, Donald Lynden Bell and Martin Rees, they thought, okay, lots of galaxies have supermassive black hole. So is it possible that our own galaxy, that is Milky Way, it can also have a supermassive black hole? But then the question arises, okay, those black holes, they are eating material and they are emitting lots of energy, and we can see those huge amount of energy. But we don't see such kind of energy in our own galaxy. So how can there be supermassive black hole? Okay, and the answer can be very simple. Like maybe there is a supermassive black hole, but it is on a diet. It is not eating anything. Okay, so maybe there is in the center of our galaxy, there is a supermassive black hole, but there is not enough material around it so that can be accreted and that can emit that huge amount of energy. So they proposed this in 1971, and that there in our Milky Way galaxy center, there can also be a supermassive black hole. But it was a very difficult task to actually prove that there is a supermassive black hole. And these two groups, one in Germany, Max Planck Institute for Extraterrestrial Physics, and led by Reinhard Genzel, and the other one in USA at the University of California, Los Angeles, led by Professor Andrea Ghez. These two groups tried to find out whether there is a supermassive black hole or not at our galaxy's center. And this effort actually led them to this to 2020 Nobel Prize, which they, like half of the prize money was received by shared by these two groups. So Reinhard Genzel, let's talk a little more about Reinhard Genzel. So he was born in Germany in 1952, and he got his PhD from University of Bonn and Max Planck Institute for Radio Astronomy in 1978. After that, he worked at Harvard Center for Astrophysics and then joined University of California, Berkeley as a professor. But in 1986, he left Berkeley and became the director of Max Planck Institute for Extraterrestrial Physics, Germany, where he's still a co-director. And the Andrea Ghez, so she is the fourth woman scientist to win Nobel Prize in Physics. Okay. And she was born in New York, USA in 1965. So from her childhood, she wanted to become the first female astronaut inspired by the moon landing, but she didn't become an astronaut, but she became an astronomer and became the not first, but fourth woman scientist to win the Nobel Prize in Physics. And she was very much inspired by her chemistry teacher, Judith Kane, and it was surprising that she was the only female science teacher she had in high school or college. So after high school, she did her bachelor at MIT and then PhD at Caltech, and now she is a professor at the University of California, Los Angeles. And apart from being an astronomer, she is also a very pro swimmer. So these two groups at one in Germany and one in USA, led by Reinhard Genzel and Andrea Ghez, they were trying to search for this supermassive black hole. They're trying to actually find out whether there is a supermassive black hole or not. Okay. But first thing is where to find it. Okay. First, we have to decide where is the center of our supermassive, center of our galaxy. So this is how our galaxy look like if you can go outside our galaxy. So this is the central region, and our solar system, or the where we are residing, is somewhere like here. Okay. Okay. So this is our solar system, and this is our galactic center. So, and this is very, very far away from us. So here you can see. Okay. So here you can see, as we are not outside the Milky Way, we are inside the galaxy. So we cannot see the spiral galaxy. We can see just this disk of this Milky Way galaxy, the plane of this Milky Way, and the night sky, it looks something like this. This is the galactic plane. Okay, and there is this Sagittarius constellation, and the galactic center is located very close to the Sagittarius constellation and is somewhere here, and it is also called Sagittarius A star. But if we zoom in to this galactic center, and then we will find like this is a very clumsy place. Okay, clumsy place. There are lots of stars, dust, gas, and many things. And if you you can zoom in very closely, then only we can see what is actually happening in the galactic center. So to find out what is there at the galactic center, we actually have to really zoom into the center to pass out all these other stars, gas, and dust. Okay. So so now they know that where is the galactic center and where to find. Okay. But how do you find a black hole? Because we cannot see a black hole just because it is black and nothing can be coming out from the black hole. It doesn't emit anything. So how do you find a black hole? And they used a very simple, like the most simple basic physics. Like we all know, just like our solar system, we all know that the planets are moving around the sun. Like this Mercury, Venus, Earth, all the planets are moving around the sun. And just by looking at the orbit of these planets, we can actually tell about the sun, like what is the mass of the sun and those things. Okay, so they actually thought, why cannot do the similar thing for the center of a galaxy? So if there is a black hole at the center of the galaxy, and if the star or whatever is there, we don't know. If there are stars, if we can find the stars which are moving around the galactic center, and if we can calculate these orbits of this star. You can see the orbit of this star. So just by looking at this orbit of the stars, we can actually say what is there, how much matter is there at the galactic center, and whether it can be a black hole or not. Okay, so this very simple method was used just the aim was to look for stars which are revolving around the galactic center, and from their orbit to find out what is there at the galactic center. Just a minute.
Lankeshwar, how far is the galactic center from us?
Okay, it is 26,000 light years away, around 26,000 light years. So light takes 26,000 years to reach from galactic center to us. It is very far away. Okay, shall I continue?
Yeah, go ahead, go ahead.
Okay, so now the idea is clear. We have to find stars which are very close to the galactic center and moving around the galactic center. Okay, but finding stars very close to the galactic center was not easy, because if we zoom in, you can see there is Sagittarius and somewhere here is the galactic center. So if we zoom into the galactic center, and in a line of sight, there are lots of dust. Okay, and this dust in a line of sight, what they do, they block the visible light. So if a visible light is emitted from a star from a galactic center, we cannot see it, because on the way to us, the visible light is scattered by the dust. Okay, but we all know, so we cannot see the stars at visible light at the galactic center, but we know that the scattering is higher for lower wavelength and is smaller for higher wavelength. So this is the reason why we see during the sunset, we see the sun in red color, right? Because the blue color, that is the small wavelength color, so they are scattered away due to the dust in our atmosphere. But the red color, which has longer wavelength, this is scattered less, and this reaches our eye. So that's why we see the sun red during the sunset. So similarly, for the galactic center, looking for the star at the galactic center, we can use the longer wavelength light, for which the scattering by the dust is less. So they just don't use red, they go to even higher wavelength to use near infrared observation, which has an wavelength around 2.2 micrometer. Okay, so this problem that there is lots of dust and the visible light cannot come to us, that is solved by going to the near infrared observation, so that the dust doesn't scatter away much of the light. So this is not only the one problem, there is a second problem. The second problem is the central part of the Milky Way is a very congested area. So there are lots of stars. So if you want to actually calculate the orbit, if you want to know the orbit of a single star, then you have to like find out the single star and you have to resolve it. If there are lots of stars, it is very difficult to find one star from another. Okay, and to resolve single star, what we need very high resolution observation. So what do we mean by resolution? So resolution is something like this. Okay, so if a car is coming to you from a very far away, so when the car is very far away, then you cannot see the two different headlights. Okay, because it is so far away, you will see this is a single headlight. So you cannot say whether this is a motorbike coming or a car coming. And only the car come very close to you, then only you can see this. There are two headlights. Okay, and this is called the resolution. So if you use a binocular, then even for a long distance, if you a telescope, even for a long distance, you can see these two different headlights. So our eye can, if it is car is very far away, our eye cannot resolve these two headlights, cannot distinguish these two headlights. So that is called the resolution, the ability to resolve two distinct lights which are very close by. So this is also true for the stars. Okay, so if there are two stars like this, and you are observing this with a telescope, and these stars are making an angle theta at the telescope. So the resolution is determined by this angle theta, at which you can distinguish these two stars. You can make out, okay, there are two stars and not a single star. And the smaller the theta at which you can differentiate between two stars, better the resolution. Okay, so to get high resolution, the theta should be small. And the theta actually depends on the diameter of the telescope with which you are observing the object. and theta is inversely proportional to the diameter of the telescope. So to achieve small theta, that is high resolution, what you have to do, you have to use very big telescope. So then, okay, we know it is clumsy, there are lots of stars, but if we can use very big telescopes, then actually we can resolve individual star and we can track their orbits. Okay, so there is this problem, there is also a solution, that we have to use very big telescopes. But that's, so what are the big telescopes that they used? So Reinhard Genzel group at first used new technology telescope in Chile, which has a, like, the mirror has a diameter of around 3.58 meter, and later they used this very large telescope in Chile, which has a diameter of 8.2 meter. And Andrea Ghez group in UCLA, USA, they used this WMK observatory in Hawaii. So there are two telescopes with which has diameter of 10 meter. So just by looking at this numbers, 10 meter or 8 meter, you may not have the idea how big the telescopes are. Okay, so let's just take a look how big actually they are. So in the left, I'm showing a telescope which in TIFR we use for public outreach to see a small galaxies or cluster of stars or nebula. Okay, so this is how you can see these small children are there, and this is the small telescope. This is how the size is. It is like a 14-inch telescope. And if you compare these telescopes with the Keck telescope that Andrea Ghez group used, a 10-meter diameter telescope, and here you can see there is a man who there, and this is the whole mirror of this telescope. So you can just see the man is sitting there. So you can just imagine compared to this how big these telescopes are. Okay, and like they are very big telescope. And these kind of big telescopes were used to observe the stars at the galactic center. But it turned out this only the big telescopes are not enough. Even there is problem with big telescopes. What is the problem? So if you use a very big telescope to observe an object, and you see, okay, you are using a very big telescope, so you should expect a very sharp and clear image. So this is expectation. But in reality, you see something like this. Okay, so it is not what you actually expect. Okay, for a big telescope, this should be expected from a small telescope. But even with big telescope, you are seeing something like this. And similarly, if there are the two separate stars which are separated by a very small distance, but even if you use a big telescope, then you expect, okay, we're using a big telescope, so we should be able to distinguish them, we should be able to resolve them. Okay, this is expectation. But even with big telescope, the reality is you see something like this, just like the headlight of the car. Okay, so even with big telescope, that cannot even the big telescope are not able to resolve this two separate study, and they show it as a single source. Okay, and what is the reason for this? We are using big telescope, but we still cannot use those high resolution. And the reason is the same as the reason for which the stars twinkle. Okay, we all know the stars twinkle, and the reason is the atmosphere in our Earth. The atmosphere is very good for us. It is atmosphere for which we are alive, but it is not good at all for the astronomers, because the starlight or light from any astronomical source is coming through the air or the atmosphere. Okay, and the atmosphere is not a very calm and still medium. It is a very turbulent medium. The temperature is changing all the time. The density is changing. The wind velocity and all this changing with time. And because of this turbulence in the atmosphere, if a light is coming from a star, what we actually see, like the position of the stars changes a little bit, and that's why you see the stars to be twinkle. And due to the same reason, this even with big telescope we cannot achieve the resolution. Okay, so this atmospheric turbulence actually limits the achievable resolution with big telescope. So this can be explained with a very good analogy. Okay, so if you go to a lake and the lake water is very calm and still, so and if you look from the top, you can see at the bottom what are there. Okay, these pebbles, these stones, you can see because the water is very still and calm. But if the water is not calm, it is flowing and there is turbulent motion, then it is very hard to see what is under the water, and you cannot see those stones. Even in this water, you can see, even in this picture, where there is the water is very still here, you can see the stones very clearly. But very close to the boat, where the water is flowing, you can see here it's like not that good. It looks like hazy. Okay, with the stones below this water, it's not that good. So this is a problem, and even with big telescope, we cannot see those stars as good as we like. Okay. So what is the solution? The solution is, one solution is speckle imaging. So what is speckle imaging? So if you are interested in photography and if you want to capture a photo of a fast moving car, so you can just click a photo and you can see something like this. Okay, you can see the car is blurred, and this is called motion blur, because the car is moving very fast, so the car will be blurred. So how will you get a sharp image of this car? So to get a sharp image, what you do, you set a very small exposure time. And if you set very small exposure time, so in that small time, the car doesn't move that much. So you get a still image of the car. Okay. So just to compare how different exposure time affects the image. So this is the image of a same waterfall, and this is at high exposure time, this is medium exposure time, and this is small exposure time. So you can see at high exposure time that it's not clear, it's like a blurred, and you cannot see exactly how the water is actually flowing. There is the overall flow, but you cannot, it is not that clear, it's not that sharp. But if you go to a smaller exposure time, it is getting sharper, and very small exposure time you can actually see how exactly the water is flowing. You can see these water droplets and those things. Okay, so to capture an image of a fast moving object, what you do, you set very small exposure time. So the same is done for speckle imaging. So due to the turbulence in the air, the what I said, that the position of the stars is moving a little bit. Okay, but this moves in a time scale of 1 second. Okay, because the atmosphere changes in a time scale of 1 second. But what is done in speckle imaging? So you take the image with exposure time of a millisecond or few milliseconds. Okay, so within that millisecond, the atmosphere is not changing that much. Okay, and so in that case, if you just the exposure time is millisecond, then this atmospheric effect will not be there. And this is such an image. Okay, of the galactic center taken with a very small exposure time of order of millisecond. But the problem is, if the exposure time is very small, you can only see the bright object, and the faint object cannot be seen. Like here, you can see this very bright object here, but there are lots of faint objects. But because of the small exposure time, you cannot see those faint objects. So what is done in speckle imaging? So you take a lots of picture with very small exposure time, and you stack them on the top of each other by looking at this big, very bright star. You just coincide the position of the bright star and stack one on the top of each other. And by stacking lots of images like this, you can get something like this. So this is after stacking a lots of small exposure image, and these are the big star, and this is actually the galactic center. And if you zoom in, you can now see these small stars. Okay, and they are not that affected by the atmospheric turbulence because each image was not affected. So this is one solution, speckle imaging, which can be used to get away this effect of turbulence and to achieve the resolution that we want. Okay, but there is even another better way, which is called the adaptive optics. Okay, so as the name suggests, adaptive optics actually means the mirror in the telescope adapts to the situation. Okay, so it looks how the atmosphere is moving, how is it behaving, and it shapes yourself. It changes its shape according to how the atmosphere is changing. So this picture actually describes the adaptive optics very nicely. So what is done? So a laser is used to create an artificial guide star. Okay, and this from artificial guide star, the light is coming. When it is coming, you can see there is a like plane wave front. Okay, but when it is passing through the air, turbulent air, due to the turbulence in the air, this plane wavefront gets distorted, and this is a distorted light, and what you receive in the telescope is the distorted light. Okay, so from this laser guide star, this distorted light is taken, and they actually in a computer they are calculate this actually how these lights are distorted. They are calculated. Okay, and according to the distorted light, we can actually change the shape of the mirror of the telescope so that this effect can be compensated. Okay? So here you can see at first the image was this rectangle, and there is this dotted line like this. Okay, and this is how the image, the telescope mirror has to be deformed to compensate for this atmospheric turbulence. So when from actual star, observing star, the light is coming, it is coming to the atmosphere, and it is again getting distorted. But now we know how the mirror has to be deformed to compensate for that. And now when the light is reflected from this deformed mirror, then it again gets back to its original form. Okay? So this is how adaptive optics works. So this is very nicely explained in this video. So just look at this video. The light is coming from the atmosphere, and due to turbulent medium, it is getting distorted. And first, it is falling onto a primary mirror of a telescope, and it is going back to a secondary mirror. And from the secondary mirror, it is going to a detector. And the secondary mirror, it is a deformable mirror. Okay. So what is done actually? So we use this sodium laser to create that guide star to actually know how exactly those air is moving. And due to the turbulence, you can see this waveform are not plain, they are distorted. But this distorted waveform are calculated using a computer, and there is a feedback circuit which is used to deform this mirror. Okay, and this mirror is deformed accordingly. And when the distorted waveform is coming, but after getting reflected from here, you can see this is coming to be plain waveform. And very small magnetic pistons are used to deform this very thin metallic mirror. Okay, so these pistons are pushed or pulled to deform this mirror, and you can see here. So once this adaptive optics is in use, you can see the improvement. With adaptive optics, the image getting lot sharper, and you can see the more detailed image. Here also, without adaptive optics, object looks like this, but when the adaptive optics is on, then you only can see, okay, there's not one star, there are two stars. And even without correction, it moves quite a lot. But with adaptive optics, you can see there is again these two objects. So using adaptive optics, we can actually achieve what is the expected resolution of a big telescope. Okay. So this adaptive optics was very much used for this project to observe the stars at the galactic center. And in this picture, you can see the adaptive optics is being used in the Cake Observatory. From these two telescopes, you can see the laser is going close to the galactic center, and in the atmosphere, it creates the guide star. And with this adaptive optics, the stars were detected. Now as we can, so now we can see the stars, and let's take a look how the stars are moving close to the galactic center. So as I said earlier, with adaptive optic off, you cannot see the stars very nicely, but when you on it, you can exactly see the resolution power goes up. So very close to the galactic center, you cannot see anything, but now you can see with adaptive optics, lots of stars are there. So now we can see the stars, and this is how the stars are moving in the galactic center. Okay, so this star mark here, this is actually the expected galactic center, and you can see all the stars are moving around it. Okay, so there are lots of stars, and the most important star for this discovery was this star with this yellow orbit. Okay, and this is called S2 star. The reason was that this orbital period of this star is very small, only 15 years. Okay, and this only 15 years, and I'll run that again. And compared to that, our sun is also moving around the galactic center, and it takes around a time of more than 200 million years to go around the galactic center. So this star, a full orbit can be seen within 15 years, and that was very encouraging. And because if we can calculate full orbit, then we can exactly know what is there at the galactic center. Okay, and if we run it again, I will run it again, and you will see. Okay, it again. So here you are seeing the time. So it starts from 1995. Okay, and goes to 1998, then 2000, and at different times how exactly the stars are moving and how the orbit is going. So it goes from 1995 to 2020. Okay, so this 25 years of hard work. Okay, not just one fine morning they found it. So 20 years of continuous monitoring and continuous observing, and only after that they are able to see one single orbit. And for the other stars, the orbit is not completed either. Okay, so this is how the stars are moving, and this is shown here again in this video. From 1995 goes to 2020, and this is very small region at the galactic center which is zoomed in quite a bit. And if we plot these orbits on a paper, and this is how the orbits look like. Okay, so it's yellow star, which is called the S2 star, Here the orbit is shown in the red. So, and this orbital period is 15 years. There are lots of other stars, though the whole orbit is not known, but using some Newton's law or Kepler's law, we can actually calculate how the orbit should be, because a huge portion of the orbit is already discovered or already observed. But this, for this star S2, the whole orbit has been observed. And just to get you to the scale, here it is like this blue at the very center, the Pluto Neptune, okay, distance from the sun to the Pluto Neptune. The solar system gets within this very small region in this, okay, very small region at the center, and compared to that, it is quite far away. Okay, so this is a very huge orbit, but still it complete its orbit within 15 years. Okay, so now we know how the stars are moving around the galactic center, but from that, what can you say about the galactic center? Okay, we know stars are moving, so what? So we can use the very basic law, okay, the Kepler's law, which Kepler was published in almost 400 years ago. And this very basic law of astrophysics can be used to say what is there at the galactic center. So this is the beauty of 2020 Nobel Prize. So though the observation and those are very challenging and very technologically involved, the basic physics is very simple. Just use Kepler's law. So what Kepler's first law says, that Kepler's law are for motion of planets around the sun. Okay, so Kepler's first law says that planets are moving around the sun with elliptical orbit, and the sun is one of its foci. Okay, so this is a typical orbit of a planet. So this is the elliptical orbit, okay, or eccentric orbit. So the elliptical orbit means it is not circular, and the eccentricity of an orbit means how much it is distorted from a circle. So for a circular orbit, the eccentricity will be 0, and as the eccentricity increases, it will be more and more distorted. Okay, so if eccentricity is very, very high, so it will be something like go like this and go to very high distance, which happens for like comets. Comets has very high eccentric orbit, so that's why they one time they come very close to the sun, but other time they goes very far away from the sun. Okay, so this is how a typical elliptical orbit or eccentric orbit around the sun of a planet looks like. So this is the blue line is the orbit, and the sun is one of these foci, and this is the another foci. Okay, and this is the closest approach where the planet goes closest to the sun. Okay, and this R is called the semi-major axis, which is half of this end-to-end distance. Okay, so if this end-to-end distance given by this red line, this smaller is half of that, which is called the semi-major axis. And but this Kepler's law is not only applicable for the planetary motion, it is also applicable for stars which are moving around the galactic center. Okay, so we see that this is from an exact paper, and you see this is how the orbit of the S2 star, or some people call it SO2 star. Okay, this is how it looks like. So you can see, if you compare to this is again an elliptical orbit, and the galactic center, the Sagittarius A star, this is at one of these foci. So that implies from this Kepler's law that it is going on an elliptic orbit around the foci. So there is an object around as the galactic center, which is controlling its movement, as sun is controlling the movement of the planets. So this some object at the galactic center is controlling the movement of these S stars. Okay, so from Kepler's first law, you know that there is some object at the Sagittarius star, and because of that, this star is moving in an elliptical orbit. And what are the orbital parameters for this orbit? For Earth, we know the orbital period is 1 year. The distance is some 1.5 into 11 meter. Okay, so for this orbit of the S2 stars, the orbital period is around 15.2 years. Okay, and the eccentricity is around 0.88. So you can see it is very deformed from a circle, and as you can see, it is not circular at all. It is highly eccentric because the eccentricity is very high. And the distance of closest approach is 120 AU. What is AU? One AU is the average distance between the sun and the earth, which is 1.5 into 10 to the power 11 meter. Okay, and at the closest distance, like here, when the star is here, and this is the galactic center, this closest distance, or the distance of closest approach, this distance is around 120 AU. Okay, and also this orbit is inclined on the sky plane at a 46-degree angle. So, but we just concentrate on these three parameters. The orbital period is 15.2 years, eccentricity is 0.88, that means it is highly deformed from a circle, and the closest approach is 120 AU. So can we say something about this central object from these parameters? Well, we can. And now we have to use the Kepler's third law. So what Kepler's third law says is T square proportional to R cube, where T is the orbital period, okay, and R is the semi-major axis. As I've said earlier in this picture, this is R, this is the semi-major axis, which is half of the end-to-end distance, the longer part of the orbit. Okay? So T square is proportional to R cube, that is orbital period square is proportional to semi-major axis cube. Okay? But if we put this constant, this is a proportionality, so we put the proportional constant, then it's something like this. T square is equal to 4 pi square divided by gm into r cube. Here g is the gravitational constant and m is the mass of the central object. So from this we can actually calculate what is the mass of the central object. And the mass of the central object only depends on this semi-major axis r and this orbital period t, as g's value is known. So the orbital period for the S2 stars, as I said, is 15.2 years, that we all know, but we don't know the semi-major axis r. Okay, but what we know is the eccentricity of the orbit and the closest approach. And from these two quantity, we can actually calculate what is this semi-major axis. Okay, r. The value of semi-major axis is closest approach divided by 1 minus eccentricity. So closest approach is 120 AU and eccentricity is 0.88. So 1 minus eccentricity will be 0.12. So the R, or the semi-major axis, will be 1000 AU. So now we know T and both R. We can put this in the formula and we can calculate the mass of the central object. And the mass of the central object is 4.3 into 10 to the 6 solar mass. So it's 4 million times massive than our sun. Okay, so that is a huge, like massive object at the center, galactic center.
Lankeswar?
Yes.
A very quick question: what does eccentricity mean? If is it close to a circle or is it very squished and a flat ellipse? Is that what you mean?
No. So eccentricity means if it is circle, then eccentricity will be 0. Okay.
Correct.
But if it is
if
flattened, more, it is more eccentric. Okay.
Okay. So that's what it is. It's saying how deformed it is from the circle.
Yes.
Okay.
Yes.
Good.
So if it is more flattened than a circle, it will be more eccentric.
Thanks. Okay.
Okay. So now we know that mass of the central object is 4 million times the mass of our sun, which is a very massive object in the center. But we started with the question that is there a supermassive black hole at our center? Okay, but we're still not there. Okay. So the question again. So is there a black hole at the center? So from this orbit of the star and from these parameters, we calculated the mass. The mass is 4.3 into 10 to the 6 solar mass. Okay, and I said earlier that anything can be a black hole if this whole matter is within the Schwarzschild radius of this mass. Okay, so for a mass of 4 million solar mass, what is the Schwarzschild radius? The Schwarzschild radius is only 0.1 AU or 0.1 astronomical unit. Again, the astronomical unit is the distance from the sun to Earth. Okay, but what only we can say that this mass is within a region of 120 AU from the orbit of S2 stars, because it can be, we don't know how extended this mass is. When it is extended up to 120 AU, we will still get an orbit something like this. Okay, so we are still not there to say yes, it is exactly, it has to be a black hole and it cannot be anything else, because the Schwarzschild radius is 0.1 AU, but we can say that okay, it is within 120 AU. Okay, but if there are other stars also, like if you look at this orbit of this S14 star, this blue orbit. Okay, so this is more highly eccentric orbit. So here again I can show you that, like for S2 the eccentricity is like 0.88. So you can see this is how it looks like. But S4 the eccentricity is more higher, maybe 0.95 or something. Okay, and you can see it is more flattened, it is more deformed than a circle. So as it is highly eccentric, it's come closer to the black hole. Okay, and for S14 the closest approach is 45 AU, and for S42 it is 120 AU, but for S14 is 45 AU. So that again means this whole mass, this 4 million solar mass, is concentrated within a region of 45 AU. but still we are around a factor of 450 off from the source radius. But still, to our understanding, there is no other object than a supermassive black hole which can have even this amount of matter within 45 AU region. Okay, so to our current understanding of our universe or the known objects, the supermassive black hole is an only option which can produce this kind of orbits and have this kind of mass within 45 AU region. Okay, so it's most likely supermassive black hole, and that's why actually Nobel Prize committee was very careful, and they said for the discovery of a supermassive compact object, they have not explicitly said this is a supermassive black hole. They said this is a supermassive compact object. This is the reason, because we are still not exactly confirmed this is supermassive black hole, but to our understanding, this is the only option. This is the only known option. Okay, so now we know that at the galactic center, what is the massive? There is a massive object, and it is most likely supermassive black hole. But what next? Can we improve more? Okay, and can we confirm this exactly? There is a supermassive black hole, not anything else. Okay, and yes, we can. So in 2019, the Event Horizon Telescope community published the first image of a black hole, or rather, the shadow of a black hole. So this is the image of the shadow of a black hole. And this black hole is residing in the center of a galaxy called M87. Okay, and they are also trying to image the shadow of the black hole at the center of our galaxy. Okay, and I think the work is ongoing, and we expect that they will publish the image quite soon, maybe within 2-3 years, or maybe even 1 year. We don't know. So once we can image the black hole at the center of our galaxy, then we can be confirmed, okay, is that a black hole or not? Okay, so this is one way to confirm that yes, it is supermassive black hole and nothing else. And there is also more. Okay, so bigger telescopes with better technology are also coming soon. So in this figure, you can see this is the Keck Observatory with current adaptive optics, and in future, the more like bigger telescope with 30-meter diameter is coming with better adaptive technology, and with that we can see stars more closer to the black hole or more closer to the galactic center and more fainter star. And with those much bigger telescope, which will be coming maybe within this decade, maybe 5-6 years, then we can actually confirm whether there is a supermassive black hole or not, because this 45 AU thing, and this will decrease if we can use bigger telescope and we can see objects which are more closer to the galactic center and more fainter object. Okay, so yes, the future is promising, and we will probably be able to confirm this exactly. This is, and probably then we can say this is not just a massive compact object. This is exactly a supermassive black hole and nothing else. Okay, so the future is very promising and bright. Okay, so with that, I will again run this very beautiful video, and just to show you this. Okay. I run this very beautiful video of this orbit of the stars again, and this shows like 30 years of very hard work of these groups. And thank you very much for your attention. Yeah, I'm done.
Thank you so much, Lankeswar. That was fantastic, and perfectly on time. It's 12 o'clock. Perfect. We have time for questions, of course. There are a couple of questions on YouTube, certainly, that I can see. We will go through them. You're okay with taking a few questions, right?
Yes.
Okay. So let's actually start at the very beginning. Let me go back and see the questions on the chat. Okay. So yeah. So one question from Sanjay is that is space-time just a mathematical model, or is there a physical existence of space-time?
Okay, probably this would have been the question for 15 November talk. Yes, so space-time is a mathematical model. Yes, so how do we answer this question?
It's a mathematical model.
Yeah, it's a mathematical question, but yeah, you can visualize it. So yes, so because you are saying, okay, I showed this picture at the very beginning. maybe the question is because of this. Okay. So actually you cannot see this with your own eye. Okay. This is a mathematical construction, and to show this you have to imagine just, okay, the space time is curved, but yeah, this is not physically, it's not like it is curved. Yeah, it is mathematical. That's to be say. Yeah.
Okay, let me take the questions which are related to the talk first. A question by Swanand is that when you were showing the, you showed this beautiful deformable mirror, etc.
Yes.
The question is, why didn't we take pictures from outside the Earth's atmosphere? Because then you don't have the problem of seeing and all that. So why didn't you take pictures from?
So there is again the limitation, like outside the Earth, the telescope we have, the biggest is the Hubble Space Telescope, okay? And it has and even with Hubble Space Telescope, we cannot get the resolution that is needed for actually resolving those small stars or close stars to the galactic center, okay? But in Earth, what we can do, we can be very big telescopes, okay? And because we don't have to send it to space, so we can be as big as you want, okay? So to get the resolution, to get the motion of the stars, we need very high resolution, and even that was not achievable with space telescopes. So we have to go with a very big telescope on the ground, and we have to somehow correct for this atmospheric turbulence, which is done with speckle imaging or adaptive optics.
Okay, so the Hubble Space Telescope is like probably 2 or 2.5 meters, and on Earth we have 10 meters. So, and given that the area goes as the size squared, so we can collect a lot more light.
Yes.
We can image much more fainter things if you can correct for the atmospheric turbulence.
Yes.
Okay, great. Let me switch to Facebook. There is a question from Akshat, who is asking, the set of adaptive optics videos that you showed, were they simulations or were they real data?
They were animation.
They were animations, but the wavefronts actually do look like that, right?
Yes. So they're animation, but you cannot see the wavefront, right? But yeah.
But there is a sensor for the wavefront. I mean, you cannot see it with your eye, but there is a sensor, and the wavefronts do look curved as they are showing in that simulation, and then they bend to the mirror. And how quickly can they bend the mirror?
Okay, they can currently they can bend at a like millisecond order time scale, but I think there is improving it to get maybe a few microsecond order time scale. So the Earth atmosphere is changing at a time scale of 1 second. Okay, so within 1 millisecond, the atmosphere is not changing that much. So even for 1 millisecond is enough for this, but if we want to go higher and higher resolution, then we may have to go to like microsecond. So for now, we can like within a millisecond, we can deform the mirror. We can calculate how the mirror has to be deformed, and then the deformation can be done in a millisecond.
Okay. A question from Harsh. Let me go back to YouTube here. These stars near the galactic center, do we have any idea if there are exoplanets around them?
No, these are very far away stars. We can just barely see them. So no, not now. We don't know whether there is an exoplanet. There may be, but we don't know.
Okay. And okay, back to Facebook. We'll take one from there. Maybe we can just go back. There are a couple of questions on black holes, etc. So might as well finish them off. Why do black holes form? I mean, I think a quick answer is please listen to the talk on 15th, our earlier talk. But can you just briefly summarize why black holes form?
So, like anything, like a star is stable because we know that gravity is trying to pull everything towards the center. Okay, but the star is stable because the star is radiating energy, and due to the energies coming from the center to the outside, there is a radiation pressure, and there is a balance between the gravitation and this radiation pressure. Okay. But at some point of time, when the star loses all the hydrogen is burned from the center, then it cannot produce any more energy, and then there is nothing to stop the gravity to the stars to collapse due to the gravity. Okay, and it goes becomes smaller. But if the mass is very small, then there is something called degeneracy pressure, which can actually counter the gravitational pull. But if the object is very massive, maybe 5-10 solar mass or more massive than that, then nothing can stop the object to collapse. So this is just because like for a huge object without any like resistance to the gravitational collapse, the gravitation pull everything to one single point, and this is how the black holes form.
Okay, very good. And a related question is, we should have expected this question to come. Is there a white hole?
Again, white hole
or is it a theoretical mathematical idea?
It's a mathematical idea for the time being.
Yeah, for the time being, we've not seen anything, and we've not. Okay, great. That takes care of that. Now, there are a few interesting questions coming in about the more specific to the talk. Why was M87, which is very far away and not in our galaxy, why was that imaged first and not SAG-A?
Okay, so as I said that the mass of our central black hole is around 4 times 4 million solar mass. Okay, but though M87 is farther away from our galactic center, it has a black hole which has a mass of billion solar mass. Okay, so that compensates because the larger black hole, the more massive black hole is more larger. Okay, so if you so it is farther away, but it is larger. So that means the bigger black hole compensates for the distance. Okay, and if you actually calculate how big it will look from the Earth, and the black hole at the center of the Milky Way and the black hole at the center of the M87, they will have the similar size because it is far away, but it is bigger. Okay, but M87, the image is already published, and but for Sagittarius A, we still don't have it. And one reason that they are saying, like, the Sagittarius is very close by, and because of that, like the Earth is moving, and because of that, and it is not a very still object. It is like moving a little bit here and there. But as M87 is very far away, it looks to be at the same position and it doesn't move compared to us. Okay, and that actually helped to capture the image of M87. But yeah, so they're also trying to publish this image or get the image of Sagittarius A star, and it will be published soon. But the answer is like the relative size of the black hole of M87 and Sagittarius A, they are similar because it is farther away, but black hole is also larger.
Okay, so I'm going to switch gears and take a question from Facebook and take a question on something different on Kepler and orbits. So Diksha is asking, is there any reason why all planets have elliptical orbits?
Okay, no, but they can have circular orbit. Okay, but circular means, okay, so I have said if the eccentricity is 0, then it is circular. Okay, but if the eccentricity is very small, like 0.0001, then you cannot differentiate. So there is no then it is very close to circle. Okay, even the Earth, for Earth or the planets around the Sun, they have very small eccentricity. For the Earth, eccentricity is, I don't know, but it is maybe 0.1, less than 0.1. Okay, it is almost circular. So it can be circular or it can be elliptical. And to show the reason, actually, yeah, with more mathematical terms, I actually can say what is the reason because of the potential well of the stars of the gravity. But yes, they can be circle or elliptical, but they can also have like non-bound orbit also, like hyperbola. Okay, but they don't get in a close orbit. They comes and they bend and they go away and they never come back. Okay, so every kind of orbit is possible, circular to small eccentric, and to going to larger eccentric orbit, and also unbound orbit, where it comes and goes away and never come back, or open orbit.
And I think this is the nice time to get to the related question. And you talked about eccentric or highly eccentric orbits and comets. Yes. A very simple thing is, why doesn't the comet, when it comes, get stuck in the sun's gravitational pull?
No, because there is angular momentum. Okay, because just remember when you there is centrifugal force, because it is moving. There is a centrifugal force. So if you if you have a rock which is bound to a rope, and if you rotate it, and it rotates, right, the stone doesn't fall off because there is a centrifugal force because of the rotation. So as the comets or planets, everything is moving. These are some angular momentum. So if we say in mathematical term, it is because of the conservation of angular momentum. But in generally, it is moving, so there is a centrifugal force. So the sun is attracting it, but the centrifugal force is counterbalancing it. So due to this, there is an equilibrium, and due to the equilibrium, there is this orbit, and it doesn't go directly into the sun.
Okay, so you always have to make sure that you conserve energy. There's kinetic
Yes.
energy and potential energy in the system, as well as angular momentum, which is because you have something rotating.
Yes.
Let's get back to the telescope as such. Okay, and the mirrors. So do you have, Akshat is asking, what type of material is most appropriate for a deformable mirror, and how is the mirror deformed?
Okay, so the mirror is, I think, for deformable mirror, they use some very thin metallic sheet. Okay, but and the mirrors are deformed with, as I've showed, there are like small magnetic piston kind of thing. In one of the video, let me go to the video. Yeah, so
Yeah.
here also you can see. So this is probably. Okay, so actually the mirror is for deformable mirror. You cannot make glass mirror, okay, because they cannot be deformed, because it doesn't because it will break down. But if you can make very thin metallic mirror, then they can be bent, because metal can be bent, and they are bent using some metallic pistons. Okay, there are lots of metallic pistons. They can push and pull on the mirror, and so this is very advanced technology. I don't know the details, but this is a basic thing. So you can see this is the thin mirror plate, and this is the pistons. Okay, and each pistons can be controlled, and these pistons push it to make it deform, or pull it. Okay, so this is how the mirrors are deformed. And for deforming mirror, we use thin metallic sheet, not glass mirror.
Oh, very good. Okay, let's get back to YouTube. Let me just see if there is anything else that I have missed. All right. Divya Shankar has a question. He says, from relativity, we know that every rotating planet has a perihelion motion, which is determined by the mass of the object at the center.
Yes.
Can't we use this to measure the mass of the supermassive object at the center of the Milky Way?
Yeah, of course you can, but the question is like the precision of perihelion, or what it means, that due to the general relativity, there is one thing called the advance of periastron. So the elliptical orbit is not at the same; it moves around. The orbit is elliptical, but it's move around. Okay? But for S2 stars, which is the closest star, even for that, this will be very small amount. Okay, so for Mercury, if you can know, for Mercury, the precision is like 43 arc second per 100 year. Okay, so yes, for S2 stars also you can measure it, but it will take long time, because with a single orbit you cannot measure how the periastron is moving. Okay, so you will search these 2-3 orbits to know, okay, previously the periastron was here, for the next orbit the periastron is here. So we have now maybe 1.5 orbit, so we don't have even 2 orbit. So once we have 3-4 cycles of the orbit, then we can use it to measure the mass of the black hole, even on the mass of the stars also. But not now. We need more time and maybe better resolution also. Maybe with 30-meter telescope, probably we'll be able to see this.
Okay, very good. Yes, this is exactly like the precession of perihelion of Mercury. Yes. Okay. Now, okay, we're getting questions on black holes. What happens if two black holes collide together, etc.? Okay, this is absolutely Lankeswar's research area, and I think he can give you an hour's talk on what happens when black holes collide together. So I think this you should send him an email, and I'm sure he will be very happy to tell you what happens when black holes collide. That's his.
Yeah, when two black holes collide, they just merge to form a single black hole, and they
emit
a very huge amount of energy.
And gravitational waves,
yes.
which Lankeswar tries and analyzes for his research. Okay, do black holes rotate about their axis?
Yes.
Okay, they do. All right, so I think it's at 12:15. We're near the end. Maybe can you just show the slide of the next Chayan Y that's coming up? Okay. So before we end. Yes. So thank you for watching, and I hope you should really watch this video of the planets going around. The stars going around the galactic center. I think it is just unbelievable that for 25 years people were painstakingly taking measurements to look at the orbits, and looking at the orbits you use something as simple as Kepler's law to get you an estimate that you have to have something really heavy at the center, and we know that it can't be a very big center, so it's got to be something like a black hole. I mean, isn't that really fantastic the way we make these inferences from the data that you get? Okay, so unfortunately, in December, we are still going to be online. So I don't think we will have our physical sessions until at least January 2021. If we are there, don't worry, we will still be online, because we know that the online audience, we can reach people all over the place. We can reach people who cannot watch it at 11 o'clock. But next Sunday, the first Sunday of December, we're going to change gears and go back into the area between biology and chemistry, which is very exciting. We have Professor Ankona from TIFR, who works on designing sensors that can be put inside cells, which can actually sense different molecules, different ions, and tell us what is happening inside a cell. So smart sensors capturing life in action. That's going to be the next Chayan Y from Ankona in the Department of Chemical Sciences, who works on these imaging things in biology. So that's again a very fantastic example of imaging. You saw imaging of the Milky Way today. This is going to be something different. But do join us and keep posting your questions. And for everything on black holes, contact Lankeswar. Lankeswar, thank you again so much. Thanks for doing this session. And thank you all for watching. See you at Chayan Y.